Hello friends, I welcome you in lecture number 3 on complex integration. In previous lecture we have discussed that how we can evaluate complex line integral, also known as contour integrals. So as we have discussed, suppose we are given to evaluate some contour integral or complex integration of some complex function f of z along contour C, then we are converting this everything in this integral into single variable, say z equal to z of t. So we put z equal to z of t, or we convert x and y in terms of single variable t, and this dz we write as dz by dt. And suppose t lies from a to b, then here we integrate from a to b. In short, we are converting our integral from two variables x and y to single variable t. Now it is not necessary that we always consider single variable as t. We can use the relationship between x and y from given curve, and we can write one variable in terms of another variable. So if I am converting y in terms of x, then here this instead of dt I will write dx, and x will lie between some two real numbers. Same thing whenever I am writing x as a function of y, then our parameter will be y. One more thing we will discuss is, suppose we have some circle with center origin and radius r, then we know its equation in the xy plane is x square plus y square equal to r square. We know that if we have a circle with center origin and radius r, this much distance is r, and center is z equal to 0, then we can write it as x square plus y square equal to r square, and we can use x equal to r cos theta and y equal to r sin theta, that is polar coordinates r and theta, to write down this circle in parametric form. So suppose z is some point on the circle, then we know that if z is any point on the circle, then z can be written as x plus iy. X is r cos theta and y is r sin theta. Therefore we can write z equal to, if I take r common, I will have z equal to r into cos theta plus I sin theta, and if I use Euler's formula, I can rewrite this as z equal to r times e raised to I theta. So this is the another form of circle in which we are writing z in terms of r and theta. R is the radius of the circle, or we know that r is absolute value of z if z is x plus iy, and absolute value of z is square root of x square plus y square, and if we square it we will get r square. So r is the radius of the circle. Now suppose we want to integrate throughout the circle. If our contour is circle starting from this point and we are moving or we are integrating along the whole circle, then we can see that we start with this point, and at this point theta is 0, and after completing whole circle we will obtain theta equal to 2 pi. So here we will consider theta as 0 less than or equal to theta less than or equal to 2 pi. So if they ask you to integrate over the whole circle x square plus y square equal to r square, then we can write in parametric form as z equal to r into e raised to I theta, where r is the radius of the circle that will be given, and our function is of only one variable theta. So depending on different values of theta, we will obtain different points on the circle. Now suppose sometimes they ask you to integrate along some part of the circle. Suppose they ask to integrate from this point to this point and in anti-clockwise direction. If we are going in anti-clockwise direction, then we have to integrate with starting point as z0. We will move along this curve, and suppose this point is z1. So at this point theta is minus pi by 2 and this point is on positive axis, so theta is pi by 2. So in that case we will write z equal to r into e raised to I theta, where theta is from minus pi by 2 to pi by 2. So this part is called right semicircle or right half of the circle with radius r and center origin. So this is parametric representation of right semicircle. So depending upon the part of the circle along which we want to integrate, we will have this change in the range of theta. So if we have right semicircle, we have theta from minus pi by 2 to pi by 2. If we have upper semicircle, we will have theta from theta equal to 0 to theta equal to pi. Suppose we want to integrate along upper semicircle, then at this point theta is 0 and at this point theta is pi. So in that case we will write this form of the circle z equal to r times e raised to I theta, where theta lies between 0 and pi. So they will specify that along which part of the circle you have to integrate, or whether you have to integrate over the whole circle, or whether you have to integrate along right semicircle or left semicircle, upper semicircle or lower semicircle. So depending upon the nature of the curve, you have to write your curve in appropriate parametric form. So here I have taken one example in which I want to integrate function z bar along the unit circle. Unit circle means circle whose radius is 1, that is r equal to 1. So we have x square plus y square equal to 1 square, that is 1, and this is called unit circle. Circle whose center is origin and radius is 1 is known as unit circle. So they will not give you the equation of the circle, they may simply write that integrate given function along the unit circle. That is, we have to integrate this function along whole circle. So we can roughly sketch. It is not necessary to sketch the curve along which we want to integrate, but it will be good if we sketch the curve. This is the center, this distance is 1 because we have radius 1 and we want to integrate along this, and this is nothing but x square plus y square equal to 1. And we know that if we consider x equal to r cos theta and y equal to r sin theta, where r is the radius and it is 1, therefore we have x equal to cos theta and y equal to sin theta. Therefore we can write z as x plus iy, that is cos theta plus I sin theta, and using Euler's formula cos theta plus I sin theta can be rewritten as z equal to e raised to I theta, and we want to integrate over the whole unit circle. Therefore theta will lie between 0 and 2 pi. If we start with this point, here theta is 0, and after completing whole circle we will come at this point again, that is we will come up to theta equal to 2 pi. So we can also observe that for this contour or curve, initial and terminal points are same, therefore it is closed contour or closed curve, and because it does not cross itself, it is simple closed contour. So it is not required to write down that this is simple closed contour, but this is just to explain that given contour is simple and closed, and rest of the things are same as we have done in previous lecture. First we denote given function by z bar, and we can write that given contour or given curve is unit circle. So we know that unit circle is given by x square plus y square equal to 1, and the parametric form of this circle or parametric representation of capital C is z equal to r into e raised to I theta. Here r is 1, therefore we have z equal to e raised to I theta, and theta lies between 0 and 2 pi. Now we will use this representation z equal to e raised to I theta. Using this we will convert f of z in terms of theta, and we will convert dz in terms of theta. So first we find out dz by d theta, because now z is a function of theta only. So derivative is exponential has derivative function itself, and using chain rule, derivative of I theta is multiplied with this and it is I, and therefore dz is I times e raised to I theta d theta. So we will replace dz by this in the given integral. And what is f of z? F of z is conjugate of z. F of z equal to z bar, and z is e raised to I theta, and we are considering conjugate of e raised to I theta, and we can write e raised to I theta is cos theta plus I sin theta, and conjugate of cos theta plus I sin theta is cos theta minus I sin theta, and this I can rewrite as, I know that cosine of minus theta is cos theta for all theta, and sine of minus theta is minus sin theta for all theta. So using again Euler's formula, if I have cos theta plus I sin theta, I can write e raised to I theta. Here instead of theta I have minus theta, so this I can rewrite as e raised to minus I theta. So this is just for understanding. If you are comfortable, you can directly write conjugate of e raised to I theta equal to e raised to minus I theta. Therefore I can write f of z is e raised to minus I theta. So f of z is also converted in terms of theta, and theta is from 0 to 2 pi. Therefore we can write our contour integral in terms of real integral in this way. Here theta has limits from 0 to 2 pi. F of z is e raised to minus I theta that we just obtained. We have also obtained dz in terms of theta. Dz is I times e raised to I theta. So here I am writing I times e raised to I theta d theta, and we can see this I is independent of theta, that I can take outside, and this is e raised to I theta, e raised to minus I theta. We can write one more step using the property of exponential function. We can write this in this form. So I will obtain e raised to 0 here, integral with respect to theta. E raised to 0 is 1, so we have to integrate 1 with respect to theta. Integral of 1 with respect to theta is theta, and limits of theta are from 0 to 2 pi. So first we put theta equal to 2 pi minus lower limit theta equal to 0. So we obtain 2 pi into I. Therefore integral of the function z bar along unit circle is 2 pi times I. This is the value of given integral. And if you observe, we have taken integral of z bar along the straight line in the xy plane. We have integrated z bar along this straight line from 0 to 1 plus I in previous lecture, that is in lecture number 2. and integral has value 1. Here we have integrated the same function z bar along the unit circle and we have different value of the integral. This means integral of same function is different along two different curves or different paths. We are integrating along contour C, and this contour C is also known as path of integration. So we can observe that integral of same function is different along two different paths of integration. So this path of integration matters in contour integrals. But for some functions, if we integrate along any path of integration between these same points, between the same initial and terminal points, then integrals remain same. So that is different story that we will discuss in upcoming lectures. And recently we are discussing that how we can obtain complex line integral of given complex function along given contour, and for that we are converting this integral from two variables to single variable, either x or y or t, and after converting everything in terms of single real variable, we are able to integrate this contour, this function easily using the rules of real integration which we have studied in our school level. So this is all about this session. I hope you like it, and we will continue with this type of problems in upcoming lectures. Thanks for watching.